In this video, we're going to learn how to solve thermal problems that involve the transfer of heat. We're going to focus on this from an IB physics perspective. So as we talk about equations that are available to you, we're talking about specifically those that are available on the IB physics SL test. Also, this is kind of assuming that we know a couple of basic facts already. You may want to take some time to look up some of the terms if you're a little lost and you haven't covered this much already. Just as a quick review, if you recall from chemistry class, when things get hot, it's just really represented by, on the molecular level, how fast the molecules are moving. The faster they vibrate, the hotter something is. Here are a list of terms that we need to know in order to talk about the things that we're going to be talking about today. I know in my classes this is something that they were supposed to read from something and kind of pick out these terms and learn what they are, but I'm going to briefly go over them. I'm not going to spend a lot of time. If you'd like to pause it and write them down, you can. So we're going to go over each one of these definitions real briefly. Thermal energy. Thermal energy is basically the total kinetic energy of the molecules, right? We were just talking about that vibrating of those molecules. And kinetic energy is the energy of motion. Heat is the internal energy that is transferred from one system to another. Heat is the most commonly misused term. We often talk about heat as in something has heat, but it doesn't have heat. Heat is something that is transferred from one object to another or from one system to another. Temperature. Temperature is a quantity that is proportional to the average kinetic energy. Okay? This is something that we need to know. It's a number that is basically saying, hey, look, on average, if we said an object is 12 degrees, that doesn't mean every molecule has the same amount of kinetic energy. So it takes all those, the molecules, different kinetic energy, some are faster, some are slower, and it's just based on the average kinetic energy that each molecule would have for that, whatever object that is that we're talking about. Thermal equilibrium is another term we're going to use, which basically means if we say it's two objects are in thermal equilibrium, that just means there's no heat flow between them anymore, that it's in a static state, right, and that they basically come to the same temperature. Potential energy, when it comes to thermal, in thermal physics, potential energy usually refers to the energy based on the intermolecular forces, like the bonds between the molecules. So in order to really increase the amount of energy stored, you have to break apart those molecular bonds, right? So, for example, you could add heat, right? Transfer of thermal energy. You can add heat to an object, or to ice, for example, and you can melt it. You can break those bonds. Internal energy is basically a term that is equal to the sum of your thermal energy, which is the kinetic energy, and your potential energy all together. Okay, now let's use these terms to go over a couple of important facts. We're going to use each one of these terms and see what happens to each one of these as we look at a couple of different scenarios. So for example, let's say we have some really cold ice. What do I mean by really cold? I mean below freezing, so negative 10 degrees Celsius. And let's say we add heat, right? That is, I'm giving it some kind of internal energy, I'm increasing its energy of some kind, either its potential or its kinetic energy. I'm giving it, its molecules, more energy. So what happens then to its temperature, the motion, and all that, okay? Well, we know that the temperature should get hotter. That's what happens. You give things thermal energy, and it's going to, or internal energy, and in this case, it'll just get warmer. If the temperature goes up, the molecules will move faster. If the molecules are moving faster, it has more kinetic energy, and kinetic energy is a measurement of thermal energy, so it has more thermal energy. But does it necessarily change its state of matter, meaning does it melt? Well, not yet, because it has to get to 0 degrees before it melts, so that stays the same. And if the bonds aren't being broken or recreated, then the potential energy doesn't change, and that's the same. Internal energy, if you recall, is the total potential plus kinetic. So this may stay the same, but kinetic goes up. Therefore, internal energy does go up, but it only goes up on the kinetic side. Whoops. It only goes up on the kinetic side. So we like to show it on this graph here. Thermal energy is or sorry, as you add heat, right, your temperature, T, capital T is temperature, as you give it more and more heat or energy, the temperature will just go up, right? And that energy goes into its kinetic energy. Okay, so let's say we now finally got to the ice up to 0 degrees Celsius, its melting point, the temperature at which it will now begin to melt. What if I got it all up to that temperature and I keep on giving it energy to its molecules? What's going to happen now? Well, I'm not sure if you're aware of this, but the only temperature in which ice and water can be at the same temperature is 0 degrees Celsius. You can have water at 0 degrees or ice at 0 degrees. So as the ice melts and you give it more energy, the ice will begin to melt, and as it melts, you'll say the temperature actually doesn't change. It'll still be 0 degrees Celsius. So the temperature stays the same. Which means the motion of all the particles, they wiggle at just the same speed. The kinetic energy, therefore, doesn't change, neither does the thermal energy, because these are all interrelated terms. We know that it'll start melting. I'm saying it goes up, whatever. It's just turning from a solid into a liquid, and that means the potential energy is the thing that's increasing. The molecules are shaking, vibrating, at the same speed, but now they're broken. They're no longer connected. They're now kind of loosely bound as water. So this means the internal energy is still going up, but this time it's in potential energy that's increasing and not the kinetic energy. Let's look back at that same graph. Now this graph is a typical graph you're going to see on a lot of tests. It's heat versus temperature. And sometimes they do time versus temperature, and they just add heat at a constant rate. So it's the same. It looks the exact same. And you can think of it the same way. So in this case, we are still adding energy, going up on the heat scale, right? We're increasing how much energy we've given it. So we're increasing the amount of energy it's received, but the temperature never goes up, right? All these stay the same because all that energy is going into breaking the bonds and going into potential energy. Sometimes we can see on the graph, like as we add energy, the temperature goes up, and therefore it must be going into kinetic. And other times we're adding energy, and temperature doesn't increase, which means it must be going into potential energy, because we're still adding energy. Let's look at some more examples. So, real fast, now let's say we melted all the water, and it's now really cold water, 0 degrees Celsius. We keep on adding energy. What will happen now? Well, it'll get warmer. Molecules will move faster, more kinetic energy, more thermal energy, but it doesn't change states of matter. It's just changing temperatures, right? So the state of matter and potential energy changes. Internal energy goes up. Same thing on the graph. Kinetic energy goes up, right? But not the potential energy. And all that energy that you add goes into kinetic. Similarly, now we get it up to 100 degrees Celsius. We keep on adding energy, right? Temperature stays the same. We're now what we call boiling or vaporizing the water. And we're turning it into a gas, right? So it changes states of matter. We're breaking bonds even further, giving it more potential energy. Internal energy goes up, right? And we're at the next plateau where we vaporize this substance. So we're going to use this graph a lot. In fact, this graph is so useful when we're doing problem solving to have in your mind when you're solving. It's almost like a free body diagram, but it's always the same graph when we're solving different problems with heat exchange. So I want you to remember this graph and keep in mind the key parts, right? When the graph is going up, the temperature is changing and all the energy is going into kinetic. When it's flat, all the energy is going into potential and it's changing phases. Now there are a couple of quick assumptions that we're going to make when we solve problems with energy heat transfer. We make a couple of simplifications to make our lives easier. For simplicity, we assume that the entire object is always the same temperature. It would involve calculus if we didn't do that. In the real world, it's possible to not have that be the case, but we're going to assume the thing eats heat slowly and evenly. We're also going to assume that you're only either adding energy strictly to kinetic or potential at a time. This isn't always necessarily the case, but in a simplistic model, it works most of the time, and it works really well again when we heat things slowly. So now we need to discuss what kind of things actually affect how much the temperature changes itself. The temperature, and in this discussion, the temperature is the only term, the only thing out of all those terms that we talked about that you can actually directly measure. So one thing, you can take a thermometer, you put it in the object, you can know how hot it is. So we want to know, how does all this energy, how does it affect how much temperature will actually go up or down? Because that's the thing we can measure. Well, let's see here. If we took a metal pot and we put some water in it and we turned on some heat, right, and we added some heat energy, and let's say we added heat energy, the same amount of heat energy to the metal pot as we do to the water, will they increase in temperature the same amounts? This is something that I don't know if you've ever done some cooking before, but you should have some experience with if you have. If you take a pot and you put it on the water or on the stove with water, after a minute or half a minute, you can take your hand, your finger, and you could dip it into the water, and it will be relatively cool or warmish. But the pot, you would not want to touch it. It's burning hot. This is for several reasons, but part of it is because the metal itself it can't take as much energy before it actually changes temperatures, where the water takes a lot more energy before it'll change temperatures. So one of the things that affects thermal capacity then, as we've seen an example of, is the material type, right? Water has a higher thermal capacity in general than metals do. But there's other things. For example, if I had a cup of water versus a quart of water and I microwave them both, you should have enough experience to know that the more water you put in the microwave, the longer it takes to really get it hot. This is because if you have the same or more of one substance and you give it the same amount of energy to both the smaller and the bigger object, so you give him the same amount of energy as him, this object should be hotter, right? Because all the energy is shared with less molecules. So each molecule gets more energy and will be moving faster. So the more substance you have also means the more thermal capacity you have as well. So as a result, we have developed two terms. Thermal capacity in general, it's just how much stuff it can take before it changes temperature. But we also want to just get in the crux of it as far as the substance itself, right? We would like to say, hey, I want to compare just water with a copper pot, right? And so then we want to say, well, I want to look at it regardless of the mass. So then we've created a new term we call specific heat capacity, which is a lot like thermal capacity, and it's specifically the amount of heat required to raise, again, 1 degree temperature, but for 1 gram or 1 kilogram, 1 common unit of mass. Okay, so specific heat is the amount of energy to change 1 degree, 1 unit, or 1 unit of mass by 1 degree of temperature. Now, specific heat, if you can just take those words, right, and you get this equation here, Q is equal to mc delta T, where C is specific heat. You can actually rearrange this, and we'll do that here in a second, and you can get this specific heat capacity. So in this equation, Q is equal to mc delta T. I hope you've seen this in your chemistry class. Q is the amount of heat, the energy you're giving an object. M is the amount of mass. Delta T is the change in temperature, and it's capital T. Don't confuse it with time. And then C is the specific heat that we were talking about. So this equation is found in your IB data booklet in topic 3, as you can see. And if you, like I said, if you kind of rearrange this and solve for C, you can always, this is a term, specific heat capacity, you need to know and you need to memorize. But if you just rearrange this equation, solve for C, and just say this in words, you now know the definition of specific heat capacity. It is the amount of Q, heat, that an object can take in order to raise, per one temperature, raise one temperature per one unit of mass. So let's practice a problem together. You can pause it and give it a try yourself just to make sure you're on the right track. This is a quick plug and chug, but there are still some common problems that students make, and it's worth our time to try it out. So let's say we have a 400 joules of heat that is added to 50 grams of copper. If the copper starts off at 15 degrees Celsius, what is the final temperature of the copper if it has a specific heat of 386 joules per kilogram per degree Kelvin? Now, one thing you will notice is that Kelvin and Celsius, they're not the same unit. Keep that in mind, but if you change 1 degree of Celsius, you've changed 1 degree of Kelvin. So the changes in temperatures can be the same amount, and that's fine. So what are we going to do to solve this? We're going to use Q is equal to MC delta T. We're just going to plug and chug. Now, this is real easy. You plug, do the math. But where do students go wrong? Well, students go wrong in the units. Okay. So for example, look at the units of C. C is in joules, kilograms, and degrees Kelvin. So in order to make this work, we need to make sure that the units, if this is what C is when we plug it in, we need to make sure the units of all these match that. So the energy is in joules. We're good. The mass is in grams. That's no good. We're going to have to convert this into kilograms first. We look at this. This is in Celsius. Well, since we're talking about changes in temperature, Celsius and Kelvin, if you change 1 degree Celsius, you've changed 1 degree Kelvin, so that's okay. So now I just need to plug and chug, and if you forget to change this to kilograms, you're sunk. It's not going to work, and it's really frustrating. Sometimes the specific heat they give is actually in units of grams, because a lot of chemistry people use grams instead of kilograms, and we do this in chemistry as well. Sometimes the energy of unit is not joules, but kilojoules or megajoules. So you have to be very careful with their units. So we're going to do some plugging and chugging. 400, right, and now we've converted this into kilograms, 0.050. Right, now we just do our simple math, rearrange. We get 20.7 is the change in Kelvin or Celsius, whatever you want. And we then want to solve for the final temperature. Don't forget, they asked for the final temperature. We just solved for the change in temperature. So we'll add the change to the original, and we'll get 35.7 degrees Celsius is our answer. So let's talk a little bit more about latent heat and what it is. Latent heat is really the amount of heat that you need to add per 1 unit of mass to undergo a phase change. And every substance has their own amounts. So for example, water, its latent heat of fusion, is 333 kilojoules per kilogram. Notice that's not in joules. The latent heat of vaporization is 2,256 kilojoules per kilogram. So in order to melt ice or in order to freeze ice, this is the one that I would end up using. If I want to vaporize ice or make it become a liquid, I can't remember what that's called at the moment, but if you condense, there we go. If you condense the gaseous, steam into liquid water, this is the one you're going to use. So on the chart, going from a gas to a liquid, like from here to here, we call that liquid to a gas is called vaporization, okay? And so we're going to use the latent heat of vaporization, but you're going to use the same L when you're going back down, okay? If you go from a gas to liquid, even though it's not called vaporization, it's called condensation, but we're still going to use the same latent heat. So latent heat fusion is used on this part here, going from liquid to solid or solid to liquid. All right, so let's take a look at this problem here. We've got 4 kilograms of water, and it's placed in a ginormous freezer. The water starts off at 0 degrees Celsius, so it's ready to be frozen. And if we remove 70,000 joules or 70 kilojoules of heat from the water, how much of this 4 kilogram water will we actually freeze? So you can try this problem yourself. It's just Q is equal to ml, plug and chug. You can pause it if you want and give it a try. Okay, so we're going to do it. Q is equal to ml. All I have to do is plug and chug. One of the problems that students have in a question like this is what they're solving for, because they give you the mass, they give you the energy, and you have the latent heat. And so the question is, what am I solving for? Well, they said how much of the 4 kilogram mass are we freezing. So that doesn't mean all of it's frozen. And remember, this M does not represent how much mass is present. It represents how much mass underwent a phase change, so how much of it froze. We don't know how much mass was frozen. We know it starts off as 4 kilograms of water. I don't know how much of that 4 kilograms was frozen, so I'm actually solving for M. That's something that students often miss. All right, so let's plug and chug. Let's look at our units, and let's decide which latent heat we're going to use. I'm going from a liquid to a solid, so I'm going to use fusion. So fusion, latent heat of fusion is 333 kilojoules per kilogram. This is 70,000 joules, so I'm going to need to enter 70 kilojoules and 333, and I just solve for M, and nice easy math. I get 0.21 kilograms of my mass. That's the only amount of mass that's actually frozen. I'm going to have to take a lot more energy out in order to freeze all of it. So when do you use each equation? So as we talked about earlier, each time that a line goes up, right, that's kinetic energy and the temperature is changing. Changing temperature means Q is equal to mc delta T. Change in temperature. That's an easy way to remember. Hey, the temperature's changing. It's on this part of the graph, right? I need to use mc delta T. Delta T is the key part. For if it's undergoing a phase change, any of these, I'm going to, Q is equal to mc delta T. I use at any of the spots, right? Now the C might be slightly different, and you can tell it is actually by the slope of the line. The slope of the line is really the C here, because the mass will be the same in each case. And so you say, whoa, wait a second. The C, so the specific heat of liquid water is different than the specific heat of frozen ice and the specific heat of vaporized gas, vaporized H2O. So we say, okay, well, what about latent heat when we're undergoing a fusion, or undergoing a phase change, excuse me. So we say, with undergoing a phase change, I'm going to use Q is equal to ml, and I can remember that because, hey, there's no delta T. I'm not changing temperatures. And just like, each specific heat is different, the length of these lines are slightly different, and so the L, the latent heat of fusion and vaporization, as we saw earlier, are not always the same. Okay, another type of problem that makes it more difficult is when you really combine multiple steps to the process. So let's say instead I'm trying to vaporize water, and I would like to know how much energy it takes to vaporize 550 grams of water if it starts off at room temperature. Now, key term, room temperature. Please note, room temperature always implies 20 degrees Celsius, or really close to 20 degrees Celsius. So if it ever says room temperature, use 20 degrees Celsius. 20 degrees Celsius or 70 degrees Fahrenheit is considered room temperature. All right, so let's say it starts off at 20 degrees. Well, how might we go ahead and solve that? Well, there's some other parts on this graph, right? There's the melting point and the boiling point, and that actually plays a role in this graph, right? The melting point is this point right here, right? The temperature at which solid becomes liquid or liquid becomes solid, right? And the boiling point is the point at which liquid becomes gas or gas becomes liquid. And so I am on the graph, I am here. I'm at 20 degrees between 0 and 100. I'm trying to get up to here. I'm trying to vaporize all of it. Right? If I'm halfway, I've only vaporized some of it. I'm trying to vaporize all this water. Well, in order to get it to vaporize, I got to get it up to vaporizing temperature, the boiling point, first. So in order to figure out the total heat, there's two steps here, right? There's the Q is equal to MC delta T part, right? I need to figure out how much energy goes into warming it up to boiling point, 100 degrees Celsius. And then how much additional heat is taken to change phases from liquid to gas. So this is really a two-step problem. So I just say, hey, look, I want to know the total heat. Q is equal to MC delta T plus ML. And I can go ahead and I can solve. So I've got my math up here, right? It's just nice, fast, simple stuff. I just want to show you a couple of tricks here real fast, right? Make sure my units are right. This is a common problem, units, especially when you're combining the two. Because look at this. First of all, we need latent heat of vaporization, right? Because we're vaporizing it. And you'll notice this is in kilojoules here. And the specific heat, the C, so the L is in kilojoules and the C is in just joules. And that's confusing. That's because latent heats are large numbers and specific heats are usually very small numbers. So we've got to make sure we get our units right. So I'm going to convert this latent heat into joules by just adding 3 more zeros before I plug it in my equation. So then I'm adding a joule to a joule. If you don't do that, you'll add a joule to a kilojoule, and then your answer will not make any sense. So we got to convert, this is in kilograms, convert this into kilograms, 0.55, and then I just plug and I chug, and I'm good. Oh, delta T, how did I know my delta T, right? Remember, I started at 20 degrees Celsius. I went up to 100, right? I need to increase by 80 in order to get to the boiling point. That's how I figured out the delta T. And then we can plug and chug, and we get apparently 1,400 kilojoules of energy it takes.